Hey, this is Ben. I'm going to go over my IQE number 7. So in this problem, we have a sphere, which is placed in stagnant air, and we need to find the Nusselt number. And for that first part of the problem, we don't need this information, but we have the Reynolds number for laminar and turbulent flow, and then the Prandtl number. So we start with our general differential equation relating the heat transfer to several different factors. And we are able to cancel out a lot of terms in this because of that first part of the problem. We're looking for a steady state. So we're left with the differential of 1 over r squared with respect to dr times k, r squared, and then dt dr equals 0. And then we have our constants, and then we can apply our boundary conditions to find those constants. So as r approaches infinity, T equals T infinity, or the temperature of the ambient air. And then we also have at r equals the capital R, T equals T of the capital R. And then we can develop our temperature profile from using those boundary conditions and constants. And from there, we can create a general equation relating the heat transfer coefficient, temperature, and diameter. And then we eventually get that our Nusselt number is equal to 2. And then for the second part of the problem, we're kind of looking at different Reynolds numbers and different types of flow. So we have this equation here, which relates the Prandtl number and the Reynolds number. And the Prandtl number is given to us, as well as the Reynolds number, and then also the ratio of viscosities. So we just plug all that information into this equation, and then we get the Nusselt numbers for the different types of flow. And then for the conceptual question, it's kind of building off the calculation question, and it's asking, what is the steady state assumption due to this problem? And it cancels, again, a lot of the things out. So there's no velocity in the differential. That all goes to 0. And then the Reynolds number in the first part of the problem goes to 0. And then in a steady state problem, when the convection and conduction are going to be equal to 0 or equal to each other at the point of the surface. So we use that relation in solving the problem. So the steady state assumption does a lot in this problem.